Hello there, children. It's time to start the next wonderful lesson for us. And that lesson happens to be Section 2.4, Zeros of Polynomial Functions. This educational experience is brought to you by your peppy friend of polynomial functions. That's me. So let's get started with this wonderful little project, shall we? Now, in order to find zeros of polynomial functions, what we're going to end up having to do is get a list of what we call rational zeros. Now, we're going to have a rational zeros test. How to do that? If you recall, P over Q. Now, P is your constant number. It's the term without the X next to it, generally speaking. It's the puny one. P for puny. It's the one that has the least amount of power there. Q is the queen. It is our leading coefficient. That is the number next to the biggest X value, or X exponent. Q being the queen, the one with the most power in all the land. Now, for our possible list of rational zeros, we take all the factors of P and divide them by all the factors of Q, and we get a big, long list of rational zeros. And then we test these zeros with synthetic division. So let us start. Alright, so first in the docket, we have a polynomial like this. X to the fourth plus 2x to the third minus 7x squared plus 8x plus 8. Now, P, what is P there? P is my end number there. That is the 8. Now, what are the factors of 8? We have a plus or minus out in front of all of them. 1, 2, 4, and 8. The numbers that multiply to 8. Q is the queen. That's a 1 there. That's just plus or minus 1. So we take all the factors of P and divide them by all the factors of Q. Well, that's just a 1. All of these numbers divided by 1 is this. Now, you could write it out as I am doing. Or what you could end up doing, this is where you have to be careful. This also equals, you have a plus or minus in front of the whole thing. Make sure you have parentheses, otherwise it's incorrect. You could have that. So, what does this mean? That's my list of rational zeros. It means if it's a rational zero, it comes from this list. Remember, rational numbers are repeating or terminating decimals. So if I said, hey, in this polynomial, is 7 a zero of this polynomial? You could immediately go, you know what, sir? No, sir. No, it is not. Because it doesn't fall in this list, and 7 is a rational number. What about a 2? And you can go, well, I don't know. It's on my list. It's possible. Let's go check it out. And we could do synthetic division, trying 2. So if it's a rational number, it must fall under this list or purview. So, what do we have next? Well, kind of the same thing, except now I put a 2 out in front of this polynomial. Well, what's it going to do to my little thing? It's not going to change my p-value at all. I'm still going to have 1, 2, 4, and 8. Those are all the factors of 8. Now, Q, I have 2 here. So, what's that mean? It's an 8, folks, sorry. That means I have plus or minus 1 and 2. So I take all these numbers, divide it by 1. No biggie. Not a big deal at all. However, Q is not only 1 this time. I have 2 factors there. So I must take all of these factors of P and divide them by 2. Here's how it works. 1 divided by 2. That's 1/2. Don't have it on my list. Need it on my list. 2 divided by 2. That's 1. Already have it on my list. Don't need to write it twice. 4 divided by 2. 2. Have it. Don't need it again. 8 divided by 2. 4. Have it. Don't need it. List complete. If you've already got it on your list, you don't need to write it twice. So that's what's great about this. So we've got that going for me. So, moving on. Now, unfortunately, we have real zeros of polynomial functions. We could also have complex zeros. What in the world is a complex zero? Well, guess what it involves? Oh yes, it involves I. So we're all happy about that, right? Yes, we are. So it involves I. We could have imaginary zeros of polynomials, not just real zeros. And we're going to go through how to construct them. So, just going through here. Look at the following. So if I have a 0 of 2, x minus 2 is a factor. The opposite of whatever my 0 is becomes my factor. If I have any 0a, x minus a is a factor. We've been over that for 2 sections now. Shouldn't be anything earth-shattering there. However, what is going to be earth-shattering for us is this. That's my complex number, a plus bi. Well, guess what? It's still x minus a plus bi there. Remember, this is my 0. The opposite becomes my factor there. Or x minus that becomes my factor. Now, you would distribute that negative if you so choose to do so. You don't have to right now, but you might eventually. So, we have one more thing to talk about with complex numbers here. We've got ourselves a theorem, kind of. It's called the conjugate pair theorem or the conjugate root theorem. Depends on which textbook you look at, what theorem you end up calling it. I'll refer to it as both in class, so just be aware of that. What this means, if a plus bi is a factor of the polynomial, it means if that's your 0 there, then a minus bi is also a factor of that same polynomial. What the heck does that mean? That means the following. Like a buy one, get one sale. If I have 7i and I say to you that's a 0, you get negative 7i along with it for free. If I have 8, that's messed up 8, plus 2i, then you get 8 minus 2i along with it. Notice here that the sign of 8 doesn't change. Only the sign of the imaginary number changes. That's something to look forward to there. That sign only changes. So, why do we know this? Because we are going to build polynomials now with our zeros. Let's start off with a basic one here. Given these zeros, write me a polynomial. Well, I know that if that's a 0, the opposite becomes my factor. If that's a 0, the opposite becomes my factor. And you get the pattern here. Now, are we done yet? No. We need to do a little FOIL action here. Little FOIL. So we FOIL the first 2 out, which yields me to this. We FOIL the second 2 out, which yields me to this. From here, we have to distribute, like we remember how to do. That means x squared to all of these items, x to all of these items, negative 12 to all of these items. You can do it one of 2 ways. You could do it the rectangular distribution way of just writing out a wonderful and glorious little chart here as such. Writing your polynomial, one of them, it doesn't matter which one you do. Like this. Writing the other one out like a grid. As such. And then just multiplying this thing out. Multiplying each thing, each item in the box. And then going through it that way. And then when you do that, now here, generally speaking, what's really neat about this, you go along the diagonals. This wonderful little creature, x to the 4th. No other friends. It's a little smaller. You go back over here, grab a new color, and go, all right, look along my diagonals. And so on and so forth. The process continues, which is really something neat if you think about it. That's if you line it up right, folks, but it's not necessarily earth-shattering if you don't. And last but certainly not least, so you got that going for you. Now, that's all well and good and swell. But what if we have the following? Now, let's say I give you one like this. A 0 of 3, 1, and 3i. Alright, doesn't seem that earth-shattering. Okie dokie. X minus 3, because my 0 was a 3. X minus 1, because my factor is a 1. x minus 3i, because my 0 was 3i. Nothing that bad. But wait, there's more. If you think about it here, we are missing something. Remember by my theorem a couple slides ago, if I have 3i as a 0, I also get negative 3i along with it for free. You have to have both. It's the conjugate pair theorem. They come in pairs. So I also get the item in green in question. Here's how to tell if you ever do it right. Folks, you never really see polynomials with i's in them, correct? As I fill this out here and I talk to you. You never see polynomials with i's in them. You just don't. So, what you've got to realize is when you do something like this, if you were to FOIL that out with just as was without the x plus 3i factor, you would end up getting some i's in my answer, which you should immediately hear warning bells in your head that it doesn't work. Now let's do a little FOIL action on the side here. X minus 3i, x plus 3i. You probably haven't FOILed out with i's in a while. First times first is x squared. Outside is plus 3ix, or 3xi, doesn't really matter. Minus 3ix plus a negative 9i squared. Well, guess what? The middle ones go away. I'm left with x squared minus 9i squared. You're like, but wait, time out, Mr. Faust, wait, sir, excuse me, sir. I said there wouldn't be any i's. And I'm not going to lie to you guys. There's an I right here. So what the heck's wrong with that? But you have to remember that I squared is negative 1. So really what I have is x squared minus 9 times a negative 1, or frankly put, x squared plus 9. Now, with this in mind, you can do the following. And when you FOIL all this out, folks, I'll save you the trouble of doing that. You end up getting the following item. And yes, unfortunately for all of you guys, you are expected to FOIL these things out. So let's work on dealing with that. There's my polynomial. If you did your P over Q list here, with that particular polynomial, factors of 27 divided by the factors of 1, that would be plus or minus 1, plus or minus 3, plus or minus 9, plus or minus 27. Look, lo and behold, that you would have seen 3 and 1 there. Now, where do these come from? Well, remember, it's a rational zeros list. 3i and negative 3i are not rational. So we will talk at great length later about how to find those. But you are ready to start off with these problems, and you will be just fine. So let us continue with that. You may proceed to the homework. Oh, happy days are here again. Woo! End.